Hello APC Mechanics students, today we'll solve the past paper FRQ 2002 exercise 2. The cart shown above is made of a block of mass m and 4 solid rubber tires, each of mass m over 4 and radius r. So m is the mass of the cart, and each tire, which is a solid rubber of mass m over 4 and radius r, and notice carefully that the masses are given in terms of each other in order to make use of the cancellation effect. Now each tire may be considered to be a disk, and they're providing for a statement, which is a disk has a rotational inertia 1 over 2 ml square, where m is the mass and l is the radius of the disk. Now here notice carefully, they're providing for you the formula, but we're not gonna use capital M, we're gonna use m over 4, which represents the actual mass of the rubber tire and the small radius r. So you can ignore this fact, and you can ignore this as well as that, and we know that the rotational inertia of the disk is given by 1 over 2 mass multiplied by radius square. The cart is released from rest, which means that initially we don't have any kinetic energy, rolls without slipping. We can make use of the fact that V is equal to omega r, the constraint equation. From the top of an inclined plane of height h, express all algebraic answers in terms of the given quantities and fundamental constants. Determine the total rotational inertia of all 4 tires. So let's start by determining the rotational inertia of one tire, and we know that inertia is an additive quantity. Then we're gonna simply multiply by 4 because we have 4 solid rubbers, although in the figure we have 2, but remember that we should think about 3-dimensional vision. Now the rotational inertia I for one tire would be half the mass, which is m over 4, multiplied by the radius r to the power of 2, and that would be 1 over 8 mr square. So this represents the inertia for one tire. Then the rotational inertia I for the system is given by 4 times 1 over 8 mr square, which is basically 1 over 2 mr square. Then the total rotational inertia is given by I, which is 1 over 2 mr square. And here no need to mention any law. Now determine the speed of the cart when it reaches the bottom of the incline, and this is straightforward. Initially we started from the point A, we need to determine the speed at the point B. Now we have friction, but it doesn't dissipate any energy because we're performing rolling without slipping. Static friction in this case would provide grip, and there is no displacement at the point of contact. So, but before we apply energy, let me say take the P level. To be the horizontal, passing through the center of mass, or to be the horizontal at the bottom of the ramp. Now here, why I avoided referring to the center of mass? Simply because from the structure of the figure, they're not interested in the center of mass. The center of mass of this cart would be with the rubbers, with the tie rubbers, it would be somewhere here, let's assume. So basically H only represents the elevation of the center of mass we are assuming. And now we can safely say apply conservation of energy. Which means energy initial equals energy final, kinetic energy initial, plus the gravitational potential energy initial is equal to kinetic energy final plus the gravitational potential energy final. Initially we don't have energy, kinetic energy, and finally we are at the PE level. So now the initial gravitational potential energy is given by mgh, and here we need to pay attention very carefully. Now m should be represent the mass of all the system. Now the system consists of 2 parts, the cart itself, which is of mass m, and the masses of the tires. Each tire has a mass m over 4, so that would be 4 multiplied by m over 4 plus m, and that would be 2m. So here we should include 2m multiplied by G multiplied by H, and the final kinetic energy, which is the tricky part. Again, we have two bodies given by the cart. Now the cart only performs translational motion, so its kinetic energy is given by half mv square. Now the tires, they perform rolling without slipping. So now we will deal with the 4 tires as if they are one tire with mass m. And because this 4 tires or the one tire, they perform rolling without slipping, which means they have 2 forms of kinetic energy. Now what is the mass of the 4 tires is given by m, because 4 multiplied by 4 over m over 4, that would be simply m, and of a total rotational inertia I. So the tires combined, they possesses 2 types of energy. One of them is given by translation half mv square, and the other one is pure rotation, which is given by half I omega square. So here let me state the kinetic energy would be half mv square for the translational motion of the cart, plus half mv square for the translational motion of the 4 tires combined, plus half I omega square, which is the rotational kinetic energy of the 4 tires combined. Now we are interested in determining the speed of the cart at the bottom of the incline or the ramp. So in this case we have 2 variables of motion, v and omega. Now omega can be changed into v by using the fact that omega is equal to v is equal to omega r, which means that omega is given by v over r, so that would be 2 mgh equals mv square if we add these together, plus half. Now the moment of inertia is given by half mr square, and omega is given by v over r, and that would be to the power of 2, and that would be to the power over 2, and we're using small r as the radius. Now this with that would cancel, and the masses would cancel as well. We have 2gh is equal to v square plus 1 over 4 v square. And remember that because v is being gained by the influence of gravity, we would expect our answer to be as a coefficient multiplied by gh. Now here in this case we have 2gh is equal to 5 over 4 v square, which means that v square is given by 8gh divided by 5. Then the speed at the bottom of the ramp is given by the square root of 8 over 5 gh. Now in part C, after rolling down the incline and across the horizontal surface, the cart collides with a bumper of negligible mass attached on idle spring, which has a spring constant k. Determine the distance xm. The spring is compressed before the cart and bumper come to rest, which is basically they're talking about the maximum compression in which we lose kinetic energy totally. Now again, this can be determined using conservation of energy. Now, so if you consider 2 points, the point here, which is the final point, and the initial point here before collision. So what's the type of energy here? Here it's completely kinetic energy, and here finally it would be completely elastic energy, which is given by half k xm square, and we're interested in determining xm. And here I'm gonna apply the following trick. Now the thing is that the form of the energy is complicated because we're talking about a combination between translational, rotation, and I'm not sure what's happening here at the surface. However, because friction is neglected along all the surface, we will do the following. So I will consider my initial point to be here of energy given by 2 mgh. All of this energy will be converted to elastic potential energy at this point, which is given by half k xm square. So again, our P level already set, and let me again say apply the conservation of energy. So energy initial is equal to energy final. Now we need to add the elastic potential energy, kinetic energy initial, plus the gravitational potential energy initial plus the elastic potential energy initial would be equal to the final kinetic energy plus the gravitational potential energy plus the elastic potential energy. Now finally, first of all, we can eliminate this. Now the initial kinetic energy is 0. The initial gravitational potential energy is 2 mgh. Now we don't have spring initially. The final kinetic energy is 0 because we're interested in the maximum compression because comes to rest. The final gravitational potential energy is 0 because we are at the P level, and that would be half kxm square. Then 2 mgh is given by half kxm square, and notice that here we cannot apply the cancellation effect for m because spring are proportional to k and independent of m, which makes m not to be cancelled. So in this case, xm square would be given by 4 mgh divided by k, which makes xm to be given by the square root of 4 mgh divided by k. Now assume that the bumper has non-negligible mass. Now here notice carefully, if you refer to the previous part, they have provided for us a given which is very important, a bumper of negligible mass. Why this is important, we will discuss in part D. Again, now our assumption would change, and the bumper has a non-negligible mass. After the collision with the bumper, the spring is compressed to a maximum distance of about 90% of the value of xm in part C. So here what they're trying to say that, suppose here we have obtained 10 centimeters. Now if you replace this bumper of part C with the new one that has mass, we will notice that the 10 centimeters would change to 9 centimeters, which is 90% of the value of xm in part C. Give a reasonable explanation of this decrease. Simply because if this bumper here has mass, so the process will have two phases. The phase one, which is governed by the linear momentum, and the second one would be the energy. Initially, we didn't talk about the linear momentum because simply the bumper has no mass, which means the phase is only, it's about energy. Now here, if it has a mass, so we need to split the phases into two. We need to do the conservation of momentum, and they would stick to each other and the speed would decrease. Unlike the conversion of complete speed in part C to xm, so here the speed would decrease before we compress the spring. So the explanation would be, since the collision is inelastic, so sum of the kinetic energy, which is basically the speed, will be lost during collision. Then the compression of the spring will decrease. And that's it for me in this video, guys. See you soon in a new one.